Good afternoon everyone. Today we will review the topic about the offline IL. So before talking about the offline IL, first I will talk about the IL in general. So in reinforcement learning, we usually formulate the problem.
Can you hear me?
Yeah, I can hear now. Can you?
So in reinforcement learning in general, we usually formulate the system as the macro-precision process, which it includes some agent and the environment. So in this setting, the agent will interact with the environment by perform an action, and then the environment will return some state and reward to the agent, and this process is repeatedly performed iteratively until some terminal point. So in the state we have the state space, which can be the discrete or the continuous state, and the action also, it can be discrete or the continuous action. And then we have the transition probability, which indicates some transition to the next state. And then we have the reward function, which depends on some state and action. The reward function is a scalar value. And in this system, the next step, because it is macro precision process, so the next step only depends on the previous step. For instance, you can see here in the step F2, it only depends on the step F1, not on the step F0. And then we also have another policy. That policy will take input as a step and output some probability over the action space. And we have the initial D0 here is the initial state distribution, which is the probability of the starting state. And D pi here is some state distribution. It means that given the policy, when we interact with the environment, we have a bunch of states, and then that state is described by some distribution. And we have another trajectory here. It means that the agent start from the state 0 and perform some action, and repeatedly until the h. H here is the length of the trajectory or the number of transitions in that trajectory. And this trajectory also has some distribution. It means that given some initial state, we perform some action, and then the environment will return some next state, and then this process is iteratively. And finally, we have the distribution of the trajectory. So in reinforcement learning, the final goal is we want to maximize the long-term reward. It means that the summation of the reward in each step, and the gamma thing here is some discounted factor to guarantee the converse. And the main target is we want to find some policy that maximize the whole reward along the trajectory. So with this target, one solution is to use the policy gradient algorithm. So what is this algorithm? This algorithm, we just take the target here as the objective function, and then we just take derivative, the gradient with respect to the parameter of the policy. Assume here that we parameterize the policy by some parameter theta, such as the neural network, and then we just directly take the derivative with respect to the parameter of the policy. And the form is like this. It's a little bit complicated, but it's just like this. And then we will use this one to update the parameter of the policy. So this algorithm is called the on-policy algorithm. This is because to optimize this objective, we need to use some on-policy data, the most recent data. So you can see in this figure, each policy in each optimized step, it outputs some data. But to optimize the current policy, it means pi k here. We just use the most recent data and we don't use the past data because this is the characteristic of this algorithm. So what's the advantage and what's the disadvantage of this policy gradient? The advantage is this method it directly optimizes the IL objective here. It means that what we want to optimize, we directly optimize that. So it is very principle and it's stable and reliable to use. But the disadvantage is it's very high variance. It means that we require a lot of sample, a lot of data to optimize, to learn the optimal policy. So many of recent paper, if we have many data, we can use this method. For instance, in the ChatGPT, they fine-tune their model by using this kind of algorithm. So another solution to solve this problem is offline off-policy actor-critic. So in the policy gradient, we directly optimize this objective. But in the offline, in the off-policy actor-critic, we indirectly optimize the policy. So first we learn some value function. That value function to quantify the quality of the policy. And then we use that function to optimize the policy. So specifically, you can see in the objective here, we given some value and we learn the value by this objective. It's very well known in the reinforcement and called the temporal reference error. And then in this objective, we try to learn the value function. And then in the next step, we will use this value function to optimize the policy here. And this process is also iteratively repeat until the end. So for more how we implement that, you can see that we parameterize the Q function by some neural network and the policy also by some neural network. And then we given some state. This state will output, the policy will output some action, and that action will put to the Q value. And then we will optimize the second objective here. So in this step, when we optimize the policy, the Q network is frozen. It means the weight is not updated. And then in the first loss, when we optimize the Q value, this one is detect. It means that there are no gradient back propagate to here, only update to here. And we usually call this one as the target or the ground truth or something similar with the supervised learning. And the data here is from some policy, and that data is like from beginning until the current step. So you can see here is the example of the how our policy use the data in this figure. So in the policy gradient, we don't use the past data, and we only use the most recent data. But here, in the our policy actor-critic, we can use also the past data. So, and typically this data usually stored in the relay buffer. And the most benefit of the our policy is it very sample efficiency. It means that it can use the past data, not only the recent data. Then it requires less sample to learn the good policy. But the disadvantage of this one is it indirectly optimizes the objective here. So in some mode, in some situation, it can be failed. It means that we cannot find the optimal policy. So now I'm talking about the offline IO. So previously I just reviewed the online on policy IO and off policy IO. So in on policy, we don't have any the relay buffer to store the past data. We just given some policy, we interact with the environment, and then we collect some data and use it to update, and then we drop this one, we ignore this one. But in the off policy, we also given some policy, interact with the environment, and then we have the data, and that data is stored in the relay buffer. And this relay buffer typically is very big, around 1 million sample. So what is the offline IO? In the offline IO, you can see in this figure, it's a little bit similar with the off policy, but we cannot interact with the environment. There are no interact with the environment here. So in the offline IO, first we can collect the data from some policy like the human or some controller, and then we store all the data in the buffer, and then we learn the policy, and finally we will deploy that to the environment. It's some kind of supervised learning. So in this setting, we also collect the state and action from some policy, and usually we don't know this policy, what is this? And the target in this setting, we also want to find the policy to maximize this objective. So what is the challenge in the offline IO is the distributional strip. So what is this? So you can see in the off policy and offline IO, it's different. But the thing here, we also have some buffer, so that we can, the very naive way is we directly apply some algorithm from off policy IO to the offline IO. And the procedure is similar. But the problem here is it suffers from the distributional shift. So what is this? So let's look detail in the first step in the policy evaluation. When you optimize this one, the Q network, the targets I override the rotation like the pi nu. So assume that in the first step, pi nu is equal to pi beta here. So there's no problem with this one. So it's similar with the supervised setting here. You can see like in the classification, we have the data and we have the round true label. And assume that it depends on some parameter used to generate the data. So at this step, everything is okay. There are no problem with this one. But because of this step, when we improve the policy, the pi nu here is changed. It's not similar with the pi beta anymore. And then the old data cannot be used for the new one. So let's see in the supervised setting, if the new data is changed, the ground truth also changed. But here, because we still use the old data, so this one will put the wrong thing. We learn the wrong ground truth. So this problem it not happen in the online IO because in the online IO we can collect more data, so it's okay. But in the offline IO, because we cannot collect more data, so it will like cause the degraded performance. So because of this problem, in the first step, we learn the Q value which is unreliable, and then it may be wrong in some region of the input. We usually call that one either overestimation. It means that in some state Ison, the value it should be like some constant, but actually we learn the higher value it incorrectly. And then because we learn the wrong Q or the unreliable Q, then in the next step when we improvement, policy maybe optimize the wrong thing, the wrong target, and then when we deploy it will like not optimal. And you can see in this equation the distributional shift only happen when we plug the input to this equation, to this Q value, and it only happens to the next action, not on the next step. So this is one problem, and another problem in the FIL is the sampling error and the function approximation error. So what is the sampling error? Sampling error means that in the training set, we have some state action, the input, but during like improve the policy, we don't have that kind of pair, that kind of input. Then we don't know what is the value for that input. So, for example, in the online setting here, the green circle is the data point, and if we have that data point, then we know the ground truth value. But in online setting, because we don't have that data point, so it is like we predict the wrong thing. And typically, this problem is always available in the online setting, but in the online setting, because we can collect more data, so it doesn't matter. So how to address that problem? You can think that it very straightforward way is during we optimize the policy, we will constrain that such that it close to the some policy pi beta here. That the policy pi beta is the behavior policy. It used to generate the policy. It is to generate the data. Then we learn that one, and then we will constrain our learn policy to close to here. So, for instance, if we given some value here, fixed state, we vary the action, and pi beta is around this. And if we don't use the constraint, the learn policy here, it can output something here, it is wrong thing. And if we constrain that, it will output something around here. So different kind of the constraint, it will cause a different method. And here is several recent methods. They use different type of constraint. For instance, in the action clipping, they first learn some pi beta and they add some noise to that, and then clip that around some epsilon to make sure that it not train too much. And another way is they use KL diversion and some another diversion they use. So one disadvantage of this method is we first need to optimize we need to learn the policy, the policy pi beta here, you mean the behavior policy. And if that's the data set is in multi-mode, and then we use a simple Gaussian policy, it will cannot fit to the multi-mode. And then two recent paper, they use diffusion model to parameterize the policy. So the advantage of diffusion model is they can capture the multi-mode very well. So most recent paper in the ICOR 2023, they use the diffusion model to parameterize the policy pi beta and also the policy pi theta here, and they learn very well. But okay, so here is some disadvantage of the policy constraint. As I mentioned, it needs to estimate the behavior of policy, and if we cannot model the behavior of policy well, so it will degrade the performance. And then one thing else is it is very conservative. So what is this? It means that we learn the policy pi theta here. It's very close to the pi theta in the distribution. So it's not really, it's too strict, and maybe it's not good. So another method is value function regularization. So in this in this family of method, they will, rather than directly constrain the policy during learning, they will constrain the value function. And then from that value function, we will derive the policy, like in this step. And this one makes the policy more freedom, not really make it close to the pi beta. So this method is less conservative than the policy constraint, since we do not limit the policy to the pi beta, and then it can perform stitching from the suboptimal behavior. So what is stitching here? So assume that you can see in this figure, in the left one, in the data we have some data set that guide from from A to B and go from B to C. Then stitching means that it can learn the good trajectory from A to C. So this is the very advantage of the value function regularization. So here is some recent method. First is the conservative Q-learning. They published in the NERIP 2022. The main philosophy of the value regularization is they put the value on the seen state action pair that put up that and reduce some unseen or uncertain state of the value to reduce that. So what the modified thing in the red line here, the standard TD error is still remain, and they put another regularizer here, want to minimize the Q for the out distribution data and want to maximize the Q for the in distribution data. It means that we have some Q value function, then we will like put up the value, we add more value for the in-state distribution, in-state data, and then we will reduce the value for the out distribution data. And then after this one, when we learn the policy, we will automatically prefer the in distribution data. And another paper is in the ICOR 2022, they use some uncertainty method to regularize the Q value. So in this method, they have some uncertainty quantification thing to measure the uncertainty of the output of the state action, and then they will use that as a regularizer, and that's when it compute like this. That's the standard deviation of the ensemble of the Q value. And another method is very simple. They also use the ensemble, but they try during optimize the Q value. They try to make the gradient of the among the Q value to diverse as possible. Okay, and here is some performance. In this,
Excuse me. Why do you want to make the gradient diverse?
So when we ensemble, if we don't make that diverse, so each element in the Q function is very similar. So the ensemble it don't have any effective. So if we make that diverse, then the Q can be very diverse, and then we can get the Q value given some input, the Q can be output very different.
I don't understand. Why do you want it different? What is this? Can you explain it this one more time? Why do you want to make it different?
So
why do you want to make it different?
We want to make it different because if we have the in-distribution data, the Q should be similar. But if we have the out of distribution data, Q should be very vary. It should be vary in the different value. So we can use that as a uncertainty thing to measure the uncertainty. So here is the comparison of the performance of different kind of method here. In this slide, I only introduce the policy constraint and value regularization, and here another method is model based. So you can see that currently the value regularization is still has a high performance. So the general philosophy of the offline different to the online is they will design some good regularization to make it the learn policy that like can close to the behavior policy but maybe better. So you can see here in the policy constraint, the general thing is we also design some regularizer here during this step, and in the value regularization we also design some regularizer here to regularize the Q function. Okay, so yeah, I finish it. Is there any question please go?
Okay, let's give big applause to the nice presentation. And feel free to throw any questions. For those in Zoom, please turn on the mic.
So
What's a question?
yes.
I want to. So does this really work for maybe for real robot or for some real application? Does it work?
Usually we want to apply this one to the situation that when we deployment, it have very high cost. So what is the example of this one? For instance, in the autonomous driving or in the healthcare system, if we deploy that in the real world, because in online if we interact in the real time, it is very costly. So this one also successful in the healthcare system and autonomous driving. And
So
yeah.
if we have lots of noise, you're saying it's not going to work. So depending on how much noise do we have, So I'm just trying to say, is this robust
Yes.
to various? And another thing that I would really like for the Q function.
Yes.
Your estimation of your Q function, is this how accurate is it?
Yes. This is one problem in the offline IO because we don't have the real data, more data, so the Q value can output the wrong thing in some regional input. So this is why they usually design the regularizer that try to reduce the Q value in the our distribution data.
Okay, thank you very much.
Any more questions? Feel free to ask any questions. Anyone?
Okay, so I can say some example about the policy gradient here because it currently used in the ChatGPT. You know, in ChatGPT we have many data, right? Many data, very huge data. So this is why they use the policy gradient rather than the policy actor critic. Because the disadvantage of the policy gradient is here because it requires many samples. So, but it's very like a directly optimized objective. So it is very stable and reliable algorithm. Yeah. That's all.
Any more questions? If not, let's give him a big applause again. Okay, thanks for participating in today's seminar, and let's meet again on next week. Thank you.